So the molecular shape and reactivity works like a lock and key. Okay? Molecular shape determines function. So this is where we talk about chemistry being our link between biology and physics. The molecular shape is a huge part of biology. Talking about hormones, talking about all of the different things in your body, your cells and how it all works, all has to do with molecular structure. For instance, the effect of cocaine on your dopamine receptors. Notice how they have the exact same pointed shape? Okay, what they do is they actually block your receptors from being able to take up your dopamine. So it keeps the dopamine in the synapse between there, which gives you the high effect. Problem is it permanently damages these over time, so you are no longer able to take up the dopamine, and your highs and lows get more and more and more extreme. But the structure of cocaine is the reason why it does this, is because it actually has a similar structure to the dopamine and is able to fill the spot where the dopamine goes. So for molecular shape, we have bonding pairs and non-bonding pairs. Okay? By noting the number of bonding and non-bonding electron pairs, we can easily predict the shape of the molecule. Electron pairs, whether they are bonding or non-bonding, repel each other. No matter what, the electron pairs will repel each other. Assume that the electron pairs are going to be placed as far apart as possible from each other. Bonding theories, the valence shell, electron pair repulsion. That name says it all. Valence shells, we're only talking about the valence shells, how those electron pairs repulse each other, push each other away in the shape that is created because of it. So that's the VSEPR theory. The valence bond theory is going to consider the valence electrons and the quantum mechanical orbitals and how they hybridize. So far, we've talked about VSEPR. All we're going to add to this is how on earth it works that we have 4 places of bonding. If our S is full and we have 4 electrons on the P, how does that work with our S and P orbitals? And we'll see the visuals behind that. So electron domains. We can refer to the electron pairs as electron domains. In a double or triple bond, all electrons shared between those 2 atoms are in the same side of the central atom, and therefore they count as 1 electron domain. So even though it's a double bond, this is still 1 domain. So on this molecule, I have 4 domains because I have a lone pair, which makes 1 domain, 2 single bonds, those are 2 more domains, and 1 double bond. So I have 4 total domains. Valence shell electron repulsion theory. This is the best arrangement of a given number of electron domains. This is the one that minimizes the repulsions. Okay, that's what happens actually in nature, so the structure that we can predict is based off of that same theory. We're going to minimize repulsions. So our electron domain geometries, those are the ones in the top block. Our electron domain geometries, we're only considering where domains are. We don't care what those domains are doing. Are they lone pairs or bonding? We don't care. All we care about is how many areas are there where they are electrons. So my electron domain geometries are only the linear, trigonal planar, tetrahedral, trigonal bipyramidal, or the octahedral. So there are 6 different domains possible. So electron domain geometries. How would the structure of CH4 and NH3 differ? Well, if we count the number of electron domains in the Lewis structure, the geometry will be that which corresponds to that number of electron domains. So CH4 has 4 domains. And H3 also has 4 domains. So if we're talking about just electron geometry, these are the same. But the visible shape we see when we zoom in on these molecules is not the same. So our electron geometry for both was tetrahedral. However, on my NH3, I don't actually see a lone pair. What I see are 3 hydrogen molecules in this pyramid shape below the nitrogen. So it's a 3-sided pyramid shape, so we call it trigonal pyramidal. So this is what you visibly see, is the 3 hydrogens on the bottom. My molecular geometry is defined by the positions of only the atoms in the molecules, not the non-bonding pairs. Okay? So for a linear electron domain, we look at our number of electron domains. We have 2. Our electron domain geometry is therefore linear. If I have 2 bonding and 0 non-bonding, well, I can't have a shape if I only have 2 atoms. 2 atoms only form a line. There is no other possible shape. 3 atoms do the same thing. If there's no other domains, electron domains, we only have a linear shape. Trigonal planar. If I have 3 total domains and all 3 of them have a bond, then my molecular geometry is trigonal planar. However, if I have 1 non-bonding, then what I visibly see is bent. So what if I have multiple bonds? What are their effects on the bond angles? In general, this is not going to be tested, but it's a basic concept. Double and triple bonds place greater electron density on one side of the atom. So if I have more electron density here, right, more electrons means more repulsion, and these are going to push on those CLs. So it pushes the 2 of these further away, which makes this bond angle smaller. Okay? So we're going to push away. If I have more electrons here, this will push on everything else. And that should make logical sense. Tetrahedral. So now I'm talking about 4 domains. If all 4 domains have an atom, it's tetrahedral. If we have 1 lone pair, trigonal pyramidal. 2 lone pairs, bent. So here's that term, account for. Remember, account for means explain. This is very much AP vocabulary. Account for each of the following observations in terms of atomic theory and or quantum theory. So I pulled out one. Boron commonly forms molecules of the type BX3. These molecules have a trigonal planar structure. This is a stated fact. What it's asking for you to do is give me some science to explain why the heck this happens. So for this would be a good answer. Boron has 3 valence electrons, each of which can form a single covalent bond with X. The 3 single covalent bonds on the boron atom orient to minimize electron pair interactions, resulting in bond angles of 120 degrees non-bonding pairs and bond angle. Non-bonding pairs are physically larger than bonding pairs. Therefore, their repulsions are greater. This tends to decrease the bond angles in a molecule. Okay, what that means here. Notice, if I have a bonding electron pair, I have positives on both ends. Both of these positive ends are pulling the electrons in an elongated structure. However, if I don't have another positive end over here, there's nothing pulling in these electrons over here at all. So instead, I have a very wide orbital over here. This wide orbital pushes on all of the other atoms of the molecule. This is why water is bent and not just linear with a lone pair on top and a lone pair on bottom. It's because I have 2 lone pairs. Each of these lone pairs take up a larger amount of area, and they push these 2 hydrogens in closer together. So notice how this angle is 104.5. Now I told you only needed to memorize the less than 120 or 109.5. Right, so we need to know that this is less than 109.5 and that is less than 109.5. These are the actual numbers. So if I have all 4 atoms, all these are equally pushing on one another, we have 109.5. If If I have one non-bonding pair on top, it pushes the other ones a little bit closer to each other. If I have two, it pushes the other ones much closer to each other. So trigonal bipyramidal electron domain. There are two distinct positions here. We have our axial, just like the axis of the Earth, and our equatorial, each of which has different bond angles. The lower energy conformations results from having non-bonding electron pairs in equatorial regions, because this is where there's more space. We just saw that non-bonding pairs take up the most space. So those non-bonding pairs, when everything's getting pushed around in this molecular structure, the non-bonding pairs go where there's the most room. We said our equatorial region has 120 degrees, whereas our axial region only has 90 degrees between itself and the equatorial region. So if the non-bonding pair is going to take up the most space, it goes where it can take up 120 degrees of space. So it goes on the equatorial region. Your lone pairs will always go on the equatorial region. So once again, 3 electron domains. We look at the amount of non-bonding to get each shape. All of these shapes should make sense based off of what you see. Octahedral, 6 total regions. Look at the number of non-bonding regions. Octahedral, square pyramidal, square plane. And then there are a couple more, but those are already on your notes. Now if we look at a large molecule, it's going to make a lot more sense to talk about the geometry of a particular atom rather than the geometry of the molecule as a whole. Because it's a huge molecule. It's usually bending on itself in different shapes and structures, and it's going to be very different for each compound, so we don't really have a naming system for this weird-looking ZLY combination thing. Instead, we look at each individual central atom. So if I look at this first central atom, it has 4 electron domains, all 4 of which are bonded. It is therefore tetrahedral. Okay. However, if I look at this carbon, 3 electron domains, and all 3 of which have an atom, trigonal planar. If I look at oxygen's electron domain geometry, it has 4. Now why does it have 4? Because notice how the lone pairs aren't drawn on here. This is normally how it's done on the AP test. They do not put the lone pairs when they're just trying to draw and show, okay, each of the atoms with the bonds. They don't have the lone pairs there. So you always have to go back and add any lone pairs. So now this tetrahedral structure makes sense. Its molecular geometry would be bent because I have 2 lone pairs, 4 total domains. Very often molecular geometry, you are given a giant organic molecule. You won't necessarily have to draw it, but you will be given the molecule and told, identify how many tetrahedrals there are. So you would need to identify how many have a tetrahedral electron geometry. So polarity. Just because a molecule possesses polar bonds does not mean that the molecule as a whole is polar. Carbon to chlorine are all polar. However, if they're all equally pulling on 4 different sides, the molecule as a whole is nonpolar. So there's a big difference between a polar bond and a polar molecule. By adding the individual bond dipoles, one can determine the overall dipole moment for a molecule. The dipole moment. Okay. That is this instantaneous. As these electrons are constantly moving, we end up with a dense area of negative charge, which gives us an overall negative area, and we call this where our dipole moment is. It's a moment of polarity as it's continually moving these electrons. So this isn't like an ion. It doesn't have a permanent negative charge. This is different. When we talk about something being polar, it just means it has a slightly negative area and a slightly positive area. The dipole moment points to where that is. Because of all of the balance of all of these electronegativities and polarities, this is where our dipole moment is occurring. So we can look at each of these different molecules and label them based off of what they are. Hydrogen chloride would be polar because our dipole moment, it's all pointing in one direction. It has to be equal in all directions. for it to be nonpolar, such as CCl4 is nonpolar. NH3 is polar. All of my dipoles are pointing towards one area, so it ends up with a polar area. This one is polar because the C's and the H's aren't polar with each other, but C to Cl is polar. So we end up with a dipole here between the C and Cl, which means that this one area ends up being negative. So overall on this whole molecule it's polar because it does have a slightly negative area and a slightly positive area. So the valence bond theory. Now we're going to take into account those SPDs and Fs and how they overlap and how they combine. Covalent bonds are formed by the sharing of electrons from adjacent atoms whose orbitals overlap. Which orbitals are involved in the bonding of the molecules shown below. So if we have atoms approaching each other, a hydrogen and a hydrogen, they overlap just their S. A hydrogen only has an S. Remember, bonding is only on the valence shell. If we have an HCl, the s orbital of the hydrogen and the p orbital of the chlorine overlap, and that's our bond. If we have a Cl to a Cl, the p of one and the p of the other overlap, and this is our bond. It is hard to imagine that from the atomic orbitals we know of s, p, our three different p's are called x, y, and z, we arise the molecular geometry we know to exist, such as tetrahedral and trigonal planar. Tetrahedral requires 4 bonding areas, but if you think of something like carbon, when we draw its molecular orbital, we say there's 2 electrons and the s, and then of my 3 p's, I have 1 here and 1 here. So how on earth is there an overlap for 4 bonds? This is what's going to be called a hybridization. The S and the P's hybrid together. So instead of having these perfect circular S and crazy 8-shaped P's, now we create hybrids that we can call SP, when an S and a P go together. So if we're mixing orbitals, consider beryllium in its ground electronic state. It would not be able to form any bonds because it has no singularly occupied orbitals. It already has full orbitals. But if it absorbs a small amount of the energy needed to promote an electron from the 2s to the 2p, it can now form 2 bonds and now has 2 open regions to form bonds. With hybrid orbitals, the orbital diagram for beryllium would not look like it normally does. Instead, the sp orbital is in a higher energy than the 1s, but lower than the 2p. Which makes sense. If we're hybridizing, we're in between the two. So instead of going 1s, 2p, we now make an sp. Okay, 1s, 2s, 2p, well now it's 1s, sp. So mixing the s and p orbitals yields 2 degenerate orbitals that are hybrids of the 2 orbitals. These sp hybrid orbitals that have 2 lobes like a p orbital. One of the lobes is larger and more rounded, like the s orbital, which makes sense. It's a hybrid. So instead of having this crazy 8, if these 2 mix together, you have this whoppy-jawed 8. You got a little tiny swirl over here and a very big one over here. When these combine, if I have an SP and an SP, these 2 combine to create what looks like a really giant p orbital. Because this little tiny bit here and this little tiny bit here don't really play much of a role. So these 2 degenerate orbitals would align themselves 180 degrees from each other, right? Negative repulsion. This is consistent with the observed geometry of beryllium compounds. Linear. Having 2 electron domains, that with each of having a bond, this would be a linear molecule. And this makes sense. If I just looked at an S, this wouldn't be possible. But by having the S and the P hybridized together to create this shape of an orbital, now it can easily overlap with the F, the P on the SF, and the P on this F to create my linear molecule. Using a similar model for boron. Okay, boron normally has 2 in the S and 1 in the P, which if I gain enough energy to promote one of these electrons into the P, I can create a hybrid of an sp2. Now this 2p is still left alone. One of these orbitals wasn't hybridized at all. It's still just existing. Okay, but this is an sp2. What this, if you count it, 1s plus 2p's, I have 3 boxes, sp2. There are now 3 places to bond on, because there's 3 domains that have an empty spot for 1 more electron. So to visualize the creation of this hybrid orbital of sp2, we take 1s, 2 of the p's, so let's say this is px and py. We take 1s, 2 p's, and we hybridize it all. So we end up with 3 of these oblong shaped of these crazy 8s, where it's what you would visually expect when you combine an S with a P. We end up with an sp2 hybrid overall when you take all of these together. To know the amount of bonding areas, we have sp2, so there's going to be a spot in the S and 2 spots in the P. So there are 3 areas to bond, which gives you this trigonal planar shape. Next, if we look at carbon, once again, looking at its regular electron configuration in orbital diagrams, it looks like it would only have 2 areas in which to bond. However, it's common we see carbon with 4 bonding areas. The reason is the S and 3 P's will all hybridize together to make an sp3, which gives you 4 locations for bonding. To visualize this, we take the S, all 3 of the P's, the P, X, Y, and Z axis P's. You hybridize all of this, you end up with 4 of these oblonged hybridized orbitals, which combined together gives you this tetrahedral shape, 4 areas of bonding. What simplifies this theory is the fact that it aligns perfectly with the VSEPR model. If we know the electron geometry, we know the hybridization. If something has 2 bonding areas, then it has an hybrid orbital of sp. If it has 3 bonding areas, it's sp2. There's 3 total areas, 1s and 2 p's. If it has 4 bonding areas, it's sp3. 1s and 3 p's adds up to our 4 different bonding areas. There are hybrids of sp3d and sp3d2. We will not spend much time talking about them, as they will not be focused on the AP test. Now to look at the bond types and how they are represented in this valence bond theory that takes the sp, d's, and f's into consideration. With these hybridized orbitals, we can also look at their ways of bonding. And the 2 ways we're going to be looking at are sigma bonding, which is end over end, and pi bonding, which is p orbitals side by side. So sigma bonding is this end over end, this overlap type bonding. Every single bond, whether it's a single, a double, or a triple, has at least 1 sigma bond, because this is the basis of bonding, where one orbital directly overlaps the end of another orbital. So this is called a head-to-head overlap. Pi bonding only applies when we have double or triple bonds. So we already have 1 sigma bond. Then a pi bond is formed around that sigma bond. So this is a side-to-side overlap, which is done by the p orbitals. A single bond is always a sigma bond, because a sigma bond overlap is greater, resulting in a stronger bond. So you won't end up with a pi bond unless a sigma bond has already been formed. Whereas when there are double or triple bonds, one of the bonds is still going to be a sigma, because it's still the lower energy, but the rest will be pi bonds, because we can't do end-to-end overlap multiple on top of each other. So the first bond is a sigma, and then the second and third would be both pi's. This is a great visual to represent this. We have our sigma bond here, this end-to-end overlap. But notice how this is a double bond. The way that is represented here is these 2 p's, this p orbital and this p orbital, have a side-to-side overlap. So this entire region is where our electrons can live. Now remember how this is a pi bond? Think of it as a really stretched out pi symbol. Notice how this doesn't change the shape overall. So we still have 3 bonding regions, which still gives us a trigonal planar molecule. And if you were to look down on this carbon to oxygen, this carbon, in fact, does have 3 bonding regions. The only thing is our double bond gives us a more dense region, which once again would push the other 2 molecules away. But this is still only 1 electron domain. I have 3 total domains. My electron geometry is trigonal planar. I have 1 atom at the end of each of those domains, so the entire geometry is trigonal planar. We know that this has an sp2 hybridization because there are 3 bonding areas, and 3 bonding areas means there is an sp2 orbital or sp2 hybridization has occurred. The last p that didn't get brought into the hybridization is what creates this pi bond. For a triple bond, we first start with our sigma bond like always, but then we have 2 pi bonds that happen at the same time. So this region here all becomes 1 pi. This and this, the up and the downward part of that p, all become 1 pi. And then this region here, sticking out at you, and the one in the far back, which obviously is going to be hard to draw in, is your other pi area. So this entire area becomes entirely encircled with a lot of electrons. However, it still is all just 1 electron domain, which gives each one of these carbons 1 domain here and 1 domain there. 2 total domains means it is a linear electron geometry, a linear molecular geometry. We have 1 sigma bond, which is where we always start, and then 2 different pi bonds, which fill out this triple bond. The resonance structures we've been using, where we represent the different areas where these pi bonds can exist, was because of these delocalized electrons. Looking at pi bonding, we can see why this occurs. In reality, instead of having a depiction where the pi bonding is only occurring here, there's oxygens on all 3 areas. Every oxygen has the same amount of electronegativity, so why is it that this one oxygen would be able to create this pi bond while the others would not? The reality is that all 4 of the atoms in the nitrate ion have their own p orbital, and the p orbitals on all 3 will overlap with the central region, which means that the electrons are delocalized. They're not occurring in only 1 pi bond, they're occurring in all of these possible regions, which is why our overall shape, one that we cannot depict with 1 Lewis structure, is that the bond length, instead of being the length of a normal double bond, becomes the length, in this case, of 1.3 bonds. Because this double bond is averaged out between all of these 3 locations. Our resonance structure tries to give us a visualization that all 3 of these must be averaged in order to see what would actually be occurring to our molecule. This concept of delocalized electrons applies to our pi electrons. These pi electrons are not localized between the nitrogen and one of the oxygens, but rather they are delocalized throughout the entire ion. To look at the molecule benzene, benzene is represented as having double, single, double, single throughout its Lewis structure. However, what we really see is we have 1 sigma bond between each one, that's always our starting, but each of these carbons still have a p that is capable of creating double bonds. But seeing as all of the carbons have equal electronegativity, the reality is that these pi bonds are formed not just between these 2, but in a uniform throughout the entire molecule, meaning that these electrons are not localized to only 1 specific area. They're delocalized around the entire area. Our resonance structure tries to represent this. The last molecular structure theory is the molecular orbital theory. This one actually considers the wave nature of electrons. So if waves are interacting destructively, the resulting orbital is going to be higher in energy. meaning if the two interact in a way that actually repels one another, we have an anti-bonding molecular orbital. If the waves interact in a way in which they can both exist in the orbital together, in other words, they interact constructively, the resulting orbital is lower in energy, and therefore a bonding molecular orbital will occur. In summary, what that's trying to say is that for atoms that have both an s and p orbital, there are two possible ways they would interact. Either the s and p that face each other will overlap in a sigma fashion, and therefore create a lower energy bond, or the sets of p orbitals will overlap in a pi fashion and create a bond, going side to side. If neither of these occur, and no bond is formed, then we call it an anti-bonding orbital. In other words, it's a full or satisfied orbital without bonding with another one. The rest of the notes for this unit take you through identifying the different properties of different compounds, which will be necessary for next week's lab. It takes you through identifying specific things about covalent compounds, which is of course what we need to know whenever we're talking about molecular geometries. There are some more notes on sigma and pi bonding, hybridization, and lastly, paramagnetism and dimagnetism. Make sure you read through, highlight, and annotate all the rest of the notes and show them to me tomorrow in class. If you have any questions, make sure to post them on Edmodo or bring them to class while we're in the computer lab.